All right, everyone can hear me well? Well, good. Okay. So I'm Mark Harris, as well as another part-time activity working on electrodynamics of the supermaterial graphene. My other major passion is astronomy, and really appreciated everyone's contributions in their papers so far in this conference. I've been an observer with the AAVSO for 15 years, and the last year or so have worked very directly with Pat Boyce's superb Boyce Astro organization. And in the audience today, my partner in crime, Robert Baker. You put your hand up, Bob. He and I have last year made a decision to wander into Speckle Interferometry, an idea actually that Dr. Alan Hale of Hale-Bopp Comet fame, he'd suggested to Pat Boyce to take another look at a system that he'd written his own PhD thesis about back in the around 1990. Dr. Hale had suggested that we take another look at 53 AQR and use some of the great Boyce Astro observatory equipment to get some good speckle interferometry measurements again of this system, particularly as it's supposed to be approaching Periastron. In other words, the two major components becoming closest together in their projected binary cycle. So this is part of confirming that this system is indeed a true binary system. So 53 Aqr AB, it's actually a potential 4-star system. A and B are very much solar-like G-class stars, G2, G3V. Discovered originally in 1800 by South and Herschel. 9 stars in the sky. The A component about 6.22 magnitude, and the B component 6.8. So nicely, easily visible in the sky. And particularly with view of doing speckle on the system that Boyce Astro has, they needed to be components ideally brighter than 12 for the 17-inch scope we're planning to use, with a separation of between 1 and 3 arc seconds. Well, the last observation that had been made at that time had produced a separation of 1.2 arc seconds, nicely within range. And we wanted to particularly view binary systems where there'd been lots of previous observations, at least 20 as a bare minimum. Well, this particular system, I think, had about 180 at the time, actually 270 observations at the time. So a good choice system for the equipment. And it's been a pleasure using the, getting to know the plane wave CDK17, a wonderful instrument, along with its great mount, L500 plane wave mount. This thing never moves unless you want it to move. The tracking is very, very good. And it's been an ideal instrument. And along with the Optech instrument rotator we have, and a very good FLI Atlas focuser, some very good fundamental equipment for this solution. I'll come back to some of the details here later, but just remember the fact that the image scale, when we've been using the Zero 1600 CMOS camera, that's our camera we've been taking these short exposure, high magnification shots with. The field of view being about 0.1 arc second per pixel. Very, very important when obviously you're trying to do some accurate measurements of a distance separation that's in that 1 to 2 arc second range. The camera is particularly good for Speckle as I go through some of the requirements of Speckle. Frame rates exceeding 200 frames per second can be done. So we're doing exposures down to as little as 5 milliseconds for these set of images. And then with using a red filter in order to maximize the efficiency of the images too. So all in all, a very good setup in terms of equipment. And the physical observatory used, the Boyce Astro Research Observatory that's just outside San Diego, was used for the images. And this particular system, 53 Aqr AB, it's in Aquarius, of course, in the northern southern sky. It just so happened all of this project coalesced with Bob and I around October, November last year. So it's perfect timing. In fact, towards the end of the timing of being able to take some good images of this particular system. So it's been mentioned a lot. In fact, some of the discussions yesterday, our high school students were talking about Speckle. So just to give a little bit more information as to what Speckle Interferometry is. So obviously one of our main problems, and certainly living in Middle Georgia, this is a year-round problem. Low altitude ground-based telescopes have always lived with atmospheric smearing. Right, you look up in the sky from Earth and you see a star and you see it shimmering. And it's all because the light is being bended at a range of slightly different angles by small cells of slightly varying density air. So you've got this ongoing problem. But there is a way around it, and Speckle Interferometry is the revolution, I think, that will enable lots of amateur and pro astronomers to get around this. Number one, take very short exposure images. So we're talking images that look just like the one on the top right there. They are just specks of a star, but the specks of the star is taken at high magnification. So that whole area of those speckles is the star that we're taking the image of. By doing this, the atmospheric induced smearing can be basically frozen. And if you take a time series of thousands of these short exposure images, one after the other, then if you can reassemble the actual real image, and I'll talk about how you do that in a minute, then you actually reconstruct the image, and the only main limitation left of the image you've reconstructed is simply the diffraction limit of the telescope. So you've eliminated that entire smearing problem, which means that ultimately, if you had a very small, 8-inch SCT telescope, you could take great speckle images. And instead of having perhaps a 1 or 2 arc-second smearing of the image, you could actually get a high magnification image showing separations of binaries down to probably 1 to 2 arc-seconds on a good night, just by using this technology. So it's a very efficient and very accurate way of distinguishing stars within the limits of your diffraction limit of your camera, not being spoiled by the variations in the density of the night sky. So as I said, well, that's what Speckle Interferometry does, but how does it actually do it? Well, by performing the Fourier transform of the triple correlation, right? That's quite a phrase, of the image set, we get what's called the bispectrum image. And the image on the left down here is the output image from some of the work that we've been doing. I'll explain about the third component later, but ignore that little third component. It's just an artifact from the artificial processing. But the two main circled stars, magenta and green, are the two main stars. That's the result of removing all that atmospheric blurring. And when I said taking the triple correlation, what you're actually doing is actually bringing, you're actually doing that Fourier transform of that entire set of images, 5,000 images in the examples we've done. And you're not just doing a correlation between an image and a copy of itself, you're actually doing the Fourier transform of the product of an image with two copies of itself. So imagine that simple Fourier transform just multiplies the similar components of multiple images to produce a much greater contrast outcome. Well, we're doing this on a triple scale with Speckle Interferometry. So that's the basic principle that gets used. And so I mentioned an 8-inch. Well, if you start doing this with the 17-inch telescope, you get an amazingly perfect outcome. I mentioned that 0.1 arc second per pixel scale. While you're trying to measure a separation of a binary, anything brighter or equal to magnitude 12 on that 17-inch telescope, you could measure the actual separation and position angle today of a binary pair down to a limit of, around about 0.1, 0.2 arc seconds. So an amazingly powerful technique. Well, what was the outcome of our measurements? We got two obviously almost identical measurements. We only measured them a few weeks apart for a binary system that's projected to have an orbit period of around anything from 600 to 3,500 years. Obviously, you're not going to get very much difference. Our biggest hindrance was the weather. San Diego weather at the time was not very helpful to us. We had a number of sessions that had to be canceled, but we got two good sessions in the end. And we measured, if you remember, I mentioned 1.2 arc seconds being the previous separation. We got 1.25, slightly larger. Position angle had increased up to around about 97.5 degrees. As I mentioned before, these are the two main star components, the primary in the middle and the secondary to the right. This is purely an artifact, and we had some experts in Speckle, people like Rick Wasson and others, take a look at our images. And basically, these are just artificial artifacts in the final image, but these are the two main stars. And then obviously, as part of the interferometry process, taking background samples as well to get the magnitudes estimated correctly too. So, so those were our main outcomes. But one of the concerning things early in our project here was we got so used to, with other star systems we studied last year, Bob and I were able to get good Gaia data on radial velocities of all the components we're trying to compare. But this particular system, in the latest release of Gaia data at the time, there was no information about the B component of the star. So we didn't have the radial velocity and parallax information that we had for the major component. The B component was missing from the data at the time. So almost the only data we originally had was our new measurements and the WDS historical data. While the historical data, certainly when you plot it, shows a nice curve on the short-term arc. There's only, a couple of hundred years of data from observations, but nevertheless, certainly tries to hint at this pair being possibly a true binary pair. There's certainly some nice movement, and it looks like it's heading towards Periastron. It's starting to curve at a sharper rate of angle change, but clearly still an uncertain binary system without additional data. Well, we actually got from, we met up over the phone with Dr. Hale and also with Dr. Rainer Anton, who've both been working heavily on this particular system. Dr. Hale, obviously going back to his original thesis, and on the right-hand side here is the original data from Dr. Hale's thesis. But luckily, even though we didn't have the Gaia data, we learned through Alan Hale and Rainer Anton that other professionals have been working hard on this system, particularly the Russian Ismailov. He'd come up with his own ephemeris projection for 53 AQR. He'd estimated the period to be around 600 years, and that the Periastron will have occurred in 2021. That was a large piece of work. Rainer Anton himself has done a lot of speckle measurements over the last 10 years or so. And also Dr. Hale assembled for us perhaps the best selection of around a dozen peer-reviewed papers over the last 20 years with good speckle measurements of this particular system. So we started assembling a lot of evidence from a lot of folks as to how likely this particular system could be considered a true binary system. And one particular ephemeris had been put together by another Russian, Tokovinin, and his particular data set had been pulled together fairly recently and was actually, as we discovered later, very close to Dr. Hale's projection. And I'll come into more of these as we progress. These became big additional items of evidence and support and data for comparison. So we ended up actually having 3 different ephemerides. That's apparently the true plural for lots of ephemerises. So we got Hale's period of 3,500 years, and Dr. Hale is projecting a Periastron 2023. And then we have the 2 Russians with their projections for a Periastron in 2021. What's particularly noticeable though is that the Ismailov one versus the Hale data just around the time of last year start really separating, meaning that the rotation, the position angle of the binary pair is really starting to swing very, very quickly on Ismailov's versus Hale's. And again, I'll come on to that in a minute. These are very significant factors. Well, what we discovered was when we started to compile our results, which is really one really new data point that was actually newer than any of the other professional measurements that Dr. Hale aided in us collating, newer than anything else that had been incorporated in any of the other ephemerides. What we discovered is, first of all, This dotted line here with all the professional measurements, our results, Harris et al., Harris and Baker, showed an extremely good correlation with those recent professional measurements. The step in the position angle was, another 3 or 4 degrees per year on from the previous results. Really just continued the same level of projection. Also, what was amazing is that the double-lined one here, the tocovinin, is incredibly close to ours and the other professional measurements. So we have a great correlation. And there's lots of other graphs that we could have pulled into the paper. This is particularly showing the position angle, but we had the same picture with the separation variation as well. So all in all, we suddenly have a new data point that's newer than anyone else's, that fits in very precisely and nicely with the tocovinin ephemeris and peer-reviewed papers of recent speckle measurements over the last decade and even before that, actually going back to the year 2000. And what's really interesting is that Dr. Hale's projection is also very similar, but just slightly different. And I think we can explain why that would be different. Whereas the Ismailov one, which is really based on a much lower period of only 600 years, really starts just moving away from all the other data sets. So at this initial stage of comparison, we came quickly to the conclusion the period must be at least around the 2,500 years projection of tocovinin based on his ephemeris data, and probably slightly less than Dr. Hale's 3,500 years. That was one obvious, easy conclusion to come to from this initial data analysis. What was really powerful to us, though, is the fact that even without the Gaia data, we could actually make a really good projection of what the orbital components would be based on other professional work that had been done alongside us. So, what really, honestly, in the preparation of this paper, it's an amazing education in the Campbell orbital elements. We've had to go back to the basic fundamental physics, so a binary star system, the strong elliptical arc, the strong elliptical arc from the historical data is a good indicator. The ephemeris that Hale had put together shows a very elongated, high eccentricity system. We have seen that in both our own data and the tocovinin data that is extremely close to Hale's data. We have data that's just added in actuals that very much reinforces the tocovinin ephemeris and is parallel and fairly close to the Hale one. So we already building evidence that this is a true binary system. For example, there is the, you can see here in the data set for tocovinin, you're seeing the theta angle increasing by 4 or 5 degrees per year. This extreme pace that's been going on paints a picture that we're close to Periastron. And here is a real find from our analysis is that the shortest separation occurred a few years ago in both the tocovinin ephemeris and in the Hale ephemeris as well. And that's significant because this is a very inclined system. And being both high eccentricity and particularly because it's inclined, we would expect the apparent periastron to occur a few years earlier than the actual periastron. And this data showing very clear apparent periastron around 2014-17 was a further indicator that this is a firstly adds further reinforcement that it's a real binary system, but secondly that the periastron should follow not that long afterwards. So that starts to build a picture together. And given the closeness of the periastron, the ephemeris of the tocovinin source compared to our own and recent professional measurements, we re-estimated the periastron based on adding our new actual data to the previous actuals and the ephemeris data of tocovinin. And we came up that the periastron actually happened in 2021.3 instead of tocovinin's 2021.1. There's still a reasonable margin of error, but nevertheless, I think the conclusion that we got from our analysis here is that actually the periastron happened probably a few months before we started our project. So we're literally at that point of periastron. Just trying to get to the next, there we go. So in conclusion, we'd both done some very good Speckle interferometry measurements. Those measurements showed a great correlation with recent professional measurements, added another new big data item in more recent times. We certainly found strong evidence that there is a great correlation with that tocovinin ephemeris, which points to a periastron around 2021. In recalculating that periastron, we found, yeah, it really did happen, we believe, by our own additional data that happened probably in 2021 as well. So overall, I think we've added more evidence that this is very likely a true binary system from a variety of perspectives. And given Hale's ephemeris is extremely close, probably the orbit period element is slightly out, but other than that, it would actually shown to be really close to recent data. Probably helps support Hale's hypothesis that binary systems comprising of solar-like G stars are often in true binary orbits, and actually helps support his hypothesis of the coplanarity of those stars as well. So it would make them great systems for hosting planets and so on. So really, really strong conclusion. Very pleased with the results. So trying to get to the next slide. Okay, so next steps, we plan to continue further studies of this system. Obviously, we're at this crucial time, given we're definitely in periastron stage, fast moving, fast changing position angles, and indeed on the separations too. So over the next few years, we plan to continue repeating these measurements. And probably I'd like to bring a new tool to the picture, and something I'd definitely like to bring into SAS as time progresses. During this project, been looking at other tools for projecting orbital elements, binary star systems. And the discovery that I've come across is perhaps the greatest mathematical advance in computing in the last 20 years. It's actually in linear algebra. That object up there is actually an elliptope, which is formed from vectors being applied to certain types of matrices. And you'll see where it intersects with the plane, actually gives you a projected elliptical orbit. And this technology has already been used in astronomy by a number of players. And that's something I'm looking to teach myself at the moment, so we can start applying that to both this project going forward and to other systems we may look at over the next few years as well. And then finally, this project was just final slide. A special thanks to many folks. This was definitely a project that did require a whole village. Dr. Alan Hale and Rainer Anton, obviously they had a great involvement in providing us with a lot of data. Dave Rowe has actually developed the software that we use to do the Speckle Interferometry, his Speckle Toolbox. Very, very powerful software. Dr. Richard Harshaw for giving us some guidance and training in Speckle Interferometry, along with Rick Wesson as well. And then National Science Foundation under award 2040433. And then Pat Boyce and Grady Boyce of Boyce Astro. Lots of training and assistance from them. And also to Kelsey Davis, who's a PhD candidate with Brown University, who acted as our scientific mentor throughout the project. So that's it, guys. Thank you.
Okay, we have time for a question or two. Was there a question online, John?
Yes, there was one. Oh, now I got a second possible one online. The first one was, I missed in the discussion. I missed in the discussion, were all the recent data gathering used using Speckle by all the observers you showed, or were there other methods used?
Yeah, it was all Speckle. We only used peer-reviewed papers of Speckle measurements. Yeah.
Another question?
You mentioned there's some other target stars you'd be interested in. Are they close to the same type of binary systems that you're observing here? Are they vastly different, or?
Yeah, we actually got another paper that Bob and I are preparing right now, using some of the latest tools, using Gaia data, different approaches to this one. So yeah, so we've got others planned, and indeed there's, I think there's even a 20, potentially 20 star system that we might be looking to analyze as well. And Speckle is definitely the tool we'll be using for that.